In the revenue generated by a person at an amusement park, we saw how S is the sample standard deviation of the residuals of the points scattered about the prediction line. But we now want to focus our attention on the true regression line for the population, which would have a y-intercept represented by alpha and a slope represented by beta. Each sample from the population would produce its own unique least squares regression line with a sample slope b sub 1. Our LSR line has a sample slope of 0.76. If we kept taking more samples, we would have various least squares regression lines with differing slopes. They would vary according to the standard error of the slope. It's like the standard error of the means, only it's much more tedious to calculate, and therefore it's going to be provided to you on an exam. Our initial slope was 0.76. Suppose the actual slope is 0.73, and our estimated standard error of the slope is 0.05. We would expect 95% of sample slopes to lie within 2 of these standard errors from the true population slope beta. Let's relate this sampling distribution of sample slopes to a coordinate axis system. Perhaps a second random sample would produce an LSR line with a slope of 0.68, and yet another sample would produce a slope of 0.72. In reality, we would not know beta. We'd like a confidence interval for what this actual population slope would equal. This works like other confidence intervals. The parameter being estimated is beta. Our sample statistic is the sample slope from the LSR line. We would use our sample slope and add and subtract the critical t-score times the standard error of the slope to construct our confidence interval.